Hello and welcome to follow my video course Introduction to Flow Mechanics. My name is Matti Ylitalo and I'm your teacher during this course. Today we will learn how we can calculate the time to empty the tank. Just a second, I'll put the presentation mode on. In this case we have a tank which is open at the top. It's filled with water and there is a tap at the bottom through which we can empty this tank. And now we want to calculate the time needed to empty this tank. Let's first think what is the pressure at the bottom of the tank. From basic physics we remember that in this kind of case when we have a water column in a tank, the weight of the water creates so-called hydrostatic pressure at the bottom of the tank. And an expression for that is simply the density of the water times the acceleration of gravity times the height of the liquid column. And from physics we remember that we have the so-called Bernoulli's equation, which is saying that the total pressure is the same everywhere. And the total pressure is the sum of static pressure plus hydrostatic pressure plus dynamic pressure. And in this kind of case, when we have open tank and we are releasing water to environment, our static pressure P1 is the same as P2. So we can drop out those from this equation. And because we don't have any inlet, our velocity V1 is 0. So what we have now is that velocity at outlet and this hydrostatic pressure. And we can calculate our outlet velocity. Typically we set our origo point at outlet level, which means that we can set H2 is 0. And then we can write an expression for our outlet velocity. This outlet velocity, so-called discharge velocity, is simply a square root over 2 times the acceleration of gravity times the liquid column height. And our volume flow out is this outlet velocity times the outlet cross-sectional area. And typically we add so-called loss coefficient to take into account the pressure loss in our outlet piping. And normally this so-called CD value is at level 0.6, 0.7. So the pressure loss at outlet piping is typically quite high. Now when we have outlet flow, there must be change in tank liquid volume. And that can be calculated as a function of change in liquid column height times the tank cross-sectional area. And because we have only one outlet, our outlet flow and change in tank liquid volume must be the same. So we can write an expression for change in liquid column height. It's quite a nice expression, except that it has this liquid column height on the right side also. If we first move our terms so that all terms related to liquid column height are on the left side and this time derivative to the right side, then we can see that if we want an analytical solution, we need to integrate, and because in our initial state we have the tank filled with water, we integrate from this water column height to 0 when the tank is empty. And at the same time, the time is running from 0 to time t, which is needed to empty this tank. And we will get an expression for that time. And it's a function of original liquid column height. But there is another way to model this case. We can use Python code to calculate these kind of cases, and we will use the same equation as a starting point. I'm using these AI tools a lot, so I asked ChatGPT to give this Python code. And I calculated an example case in which the tank diameter is 1 meter, tank liquid height is 1 meter, and there is an opening which has a diameter 25 millimeter. And based on this result, it seems that it takes around 60 minutes to empty the tank. And in this picture you see also the analytical results, and it seems that both analytical and these numerical results are exactly the same. If you have a CFD tools like Fluent or OpenFOAM, you can test what is the effect of viscosity. Calculate first with water and change the liquid to high viscosity oil. Look at what is the difference in time to empty the tank. Also you can test a case when you close that at the tank top and push some pressurized gas above the liquid level. Look at how it affects on time to empty the tank. And you can make a detailed simulation of outlet also. There is one very interesting case to be calculated. If you want to fill this tank from the bottom, then you will have almost a similar kind of mathematical problem. But now you are working with pressure difference. Pressure difference between your pump outlet pressure and this hydrostatic pressure. And finally you will be in a situation that the hydrostatic pressure at the bottom of the tank is the same or even higher than your pump outlet pressure, and then this process will stop. Here is an example calculation. If your pump outlet pressure is 2 bars, the maximum height of the water column is around 20 meters. Then the process will stop. Okay, that was all this time. Thank you for watching, and in next video we will move to heat transfer cases. See you. Bye bye.